Antonio for this kind of opportunity, and I changed a little bit the name, the title of the talk. I will speak about the Fano effect from light, I mean, in a system where plasmons, I mean, mixed excitations, light and electrons, play a role, and also in acoustic. So this is the outline. I will discuss Fano terahertz effect in this kind of interesting materials, three-dimensional topological insulators. In particular, I will discuss the Fano effect due to the interaction between a photon in three-dimensional topological insulator and the plasmons at the surface due to the Dirac carriers. And also I will extend the discussion to the out equilibrium Fano effect, where topological insulators are pumped by an optical femtosecond pulse. The last part of the talk will concern probably one of the first evidence of Fano interactions in acoustics, in sound, and in particular I will discuss the Fano some effect of the sound emissions in a particular form of three-dimensional graphene, and also the Fano effect that we observed very recently in that system. So I have no time for discuss very deeply the physics behind the topological effect in some materials. Probably the most famous three-dimensional topological insulator is this one, bismuth selenites, and this kind of material, for example, antinomium selenites and other bismuth tellurides, are intrinsically stratified material having a metallic surface. The thickness is more or less around 10 nanometers or less, and an insulating bulk. The bulk can be described by a bulk band insulator with a Schrödinger quadratic dispersion, energy versus momentum, and the gap is of the order of 300 MeV. On the other hand, the surface is characterized by Dirac electrons. This is the second case after graphene, where Dirac electrons have been discovered in solid-state materials, and you have a lot of properties. For example, in the interaction between an electromagnetic field and Dirac electrons at the surface of bismuth selenite, you have a specific exotic terms that in high energy field is physics is called the axionic term. It's just the scalar product between the magnetic and the electric field. Topological insulator may host superconductivity, and probably there are some evidence of Majorana fermions. Anyway, this is the situation. So the main ingredient concerning the topology, the exotic topology, is the strong spin-orbit coupling that render insulating the bulk, and you have Dirac carriers with a intermediate density at the surface, around 10 to the 13 electrons per centimeter square. This is probably one of the first photoemission evidence of Dirac cones at the surface of bismuth selenites. You see that you have also some contribution from Schrödinger electrons at the surface due to the so-called band-bending effect. And this situation can be, improved by using thin films grown by molecular beam epitaxy technique. Actually, what about the low energy electrodynamics? Most of the low energy properties are related to the terahertz range. 1 terahertz is 33 centimeters minus 1 and corresponds to 80 millieV and 300 microns in terms of the wavelength. Actually, we measure thin films grown on a sapphire substrate. Probably is the best substrate, dielectric substrate, in order to grow high quality system. So you have two metallic surface, the insulating bulk, D is the thickness. You can measure the transmittance by illuminating by terahertz radiation this structure, and you can accede to microscopic information about the conductance or the optical conductivity. If you plot the conductance, you see that you have at a low frequency, the terahertz range, a contribution that does not depend on the thickness. This means that you have a surface conductivity, and a phonon coming from the bulk that increases by increasing the thickness. If you have a metallic surface characterized by an electron gas, you also have some, collecting modes, the plasmon. So in order to excite a plasmon by radiation, you need to patterning the surface, because if you plot the dispersion, omega versus the momentum, the red curve corresponds to the plasmon dispersion at the surface, and the dashed line is the light. So in order to excite a plasmon, you need an extra momentum, and this extra momentum is provided by a patterning of the surface. Actually, we pattern the thin film surface of bismuth selenites by different structure, ribbons, disc, rings, and I will show you some examples of plasmon and Fano interaction in that case. This is the situation for an array of ribbons where we change the thickness of the ribbon, W, from 2 microns to 20 microns. These micrometer sites provide in the dispersion curve plasmons in the terahertz range. So you can change the energy of the plasmon by changing the size of the patterning. This is in general in plasmonic, most of the electrodynamic response is plotted in terms of the extinction, and the extinction is just 1 minus the transmittance. And the blue curve at a low temperature is the extinction of a non-patterned film with a thickness of nearly 60 nanometers. So this is drew the term and superimpose the phonon of the bulk. When you pattern by ribbon arrays and changing the size of the ribbons, you see that if you measure the extinction with the light polarization parallel to the ribbons, charges are not localized, are not confined, so you have a Drude response in that case. And you see that this response is very similar to the non-patterned film. Actually, if you change the polarization, the light polarization is perpendicular to the array, you can excite plasmons, and the extinction response is very different with respect to the parallel contribution, and you see that you have a two peaks response. Actually, the very interesting property is that at the spectral location of the phonon, around 2 terahertz, you see a minima for any patterning. We explain this behavior in terms of a Fano interaction between the phonon and the plasmon, because the plasmon and the phonon in that case are at the same energy, more or less, and so you can excite by light directly the plasmon, directly the phonon, and the phonon and the plasmon talk about with a specific interaction. This kind of a scenario can be described in terms of the standard, classical theory of Fano, and if you fit the experimental extinction by the Fano formula, you can extract the bare plasmon excitation. The data are the blue points, the phono is located around 2 terahertz, and the red curve that shifted by decreasing the size is the bare plasmon. If you plot the central frequency of the bare plasmons versus the wave vector, the wave vector is determined, if you remember, by the size of the ribbon. So changing W, you can sampling the dispersion. If you plot the dispersion, you have the red point. This is the frequency, the plasmon frequency versus the wave vector. You have the red point, and if you calculate the dispersion, the theoretical dispersion of the Dirac plasmon at a low wave vector that depends only on the density, Dirac density at the surface and on the electric function at the interface, air and sapphire, and on the Fermi velocity, all these parameters can be determined by different experiments. So you calculate the dispersion for fixed physical parameters, you have the black dashed dispersion. So the Dirac dispersion, calculated Dirac dispersion, starting from physical parameters, exactly reproduce experimental data. So plasmon are due, in that case, by Dirac carriers at the surface. You can change the structure. For example, in rings, you have, this is the extension of the ring, you have a three-peak structure, and this three-peak structure, due to a different, plasmon excitations, in general a ring sustain two different plasmon, an antibonding plasmon where the charge excitations are in antiphase, and a bonding plasmon where the charge excitations are in phase. Actually, the bonding plasmon hybridized with the phonon, Fano interacting with the phonon, so you have a three-peak structure. The high frequency peak is due to the bare antibonding plasmon, which does not interact by Fano mechanism with the phonon, and the bonding plasma at low frequency, which interacts by the Fano mechanism with the back phonon. This is another case of Fano interaction in topological insulator. This is the last example in topological insulator. If you create an out of equilibrium electron density by pumping with an optical pump above the insulating gap, and you probe the plasmon, the out of equilibrium plasmon, by a terahertz femtosecond probe, you observe a dynamical modulation of the Fano. Here I plot the relative variation of the transmittance of your films by changing the delay between the pump and the probe. By following in time the pumping, you increase the number of electrons in the Dirac bands, so you increase the density of the frequency of the plasmon excitations. So the plasmon shift in time. Okay, the plasmon hardens by increasing the time because you feel the Dirac bands, and when the central frequency of the plasmon shift below the phonon, you change the dip, the Fano interaction. This is a dynamical mechanism in order to modulate the Fano interaction by changing in the femtosecond scale the Dirac density. Actually, I change now completely the argument because very recently we start to work on very exotic structure of the graphenes. We start of two-dimensional graphene, and with our collaborators produced three-dimensional structure. Here you see an example of this, the three-dimensional structure based on the two-dimensional graphene. This is a sponge. The density of this sponge is very, very low, comparable to the air, so you have actually an effective medium system in which the content of air is around 99% in weight. This material is very interesting because locally you have a two-dimensional graphene. In particular, in that case, you have a nearly non-doped two-dimensional graphene with a very high content of air, and this system, for example, is very, very elastic. You can compress the sponge and you remain in the elastic region up to a compression of the order of 90%. If you relax the compression, you recreate exactly the same structure. Actually, why it should be interesting? So this is an example of, music produced by graphene, by this kind of graphene. First I show you the experiment. So this is the graphene. Here you have a light, and this is a microphone in order to record the sound. This is Neil Young, probably you know, is a songwriter, Canadian songwriter. So, the idea is the following. We use an audio file, voltage versus time, and with this audio file we modulate the light coming from a source. In that case, it was a diode emitting source, okay, indivisible. In that case, the light is actually, the intensity of the light maps one-to-one the acoustic file, the sound file coming from the audio file. So the intensity arrives to the sample, and graphene produces itself the sound. It is a kind of a transducer, light to sound. This effect was known since two centuries, and is called photoacoustic effect, discovered by Bell in 1885 in gases. Actually, the idea is why the graphene is three-dimensional graphene works very well. It's a very high fidelity loudspeaker in that sense, because you have a lot of specific quality of two-dimensional graphene which add together in order to reproduce the sound when you excite the graphene sponge by light. Actually, the main point is that we start from a non-doped graphene, so the absorption coefficient is nearly constant from megahertz to ultraviolet. So this means that if you excite electrons, in that case the system responds in the same way from megahertz to ultraviolet. When you excite electrons, for example by visible light, you have, this is a very interesting characteristic of two-dimensional graphene, a rapid transfer of the electronic absorbed energy from the radiation absorbed energy from electrons to phonons. This is a characteristic of graphene. You have practically not re-emission in energy in terms of radiative emission. So in that case, you create a out equilibrium phonon out equilibrium phonon C, and most of the energy of the phonon diffuse very rapidly in graphene because the thermal diffusivity is very high in two-dimensional graphene. The third point is that the heat capacity of graphene is nearly zero. So this means in a very rapid temporal scale, most of the energy coming from light is transferred to the air around graphene. In particular, if you have a sponge graphene where the air content may reach the 99%, you have a very effective transfer of energy from light to a thermal wave. This phenomena is an adiabatic phenomena, so the thermal waves corresponds to a pressure wave. This means it corresponds to sound. Just the last two slides, we have a lot of idea for using this mechanism, in particular for measuring, for using for the graphene sponge for terahertz detector. Terahertz is a very important region now in the electromagnetic spectrum, and for example, we measure that the sound emission is practically linear by changing the pulse energy in a femtosecond terahertz laser. And also for high fidelity loudspeaker, we compare the graphene loudspeaker with probably one of the best commercial loudspeaker, and the fidelity is higher in graphene sponge. Just the last slide. Very recently, I mean last week, we observed also probably one of the first example of acoustical Fano effect. When you excite the graphene sponge by light, you can modulate the intensity with a different, light temporal structure. For example, in that case, we illuminate the graphene by an impulsive light that corresponds in frequency to a background, and a sinusoidal light, that means a monochromatic light. So the sound as produced corresponds to an interaction between the monochromatic sound with the background, and this interaction determines a Fano profile of the sound, the total sound emission. You can see that if the sinusoidal light is around 200 Hz, you see a Fano profile with a deep high frequency that corresponds that this light, this sound interacts with the low energy, the low frequency sound background here. When you increase the modulation of the light, the profile show a deep low frequency. That means that at 300 Hz, this monochromatic sound interacts mostly with a high frequency background. When you increase a lot the frequency, you see that you recover a non-Fano profile. So I would like to thank a lot of people for Plasmonics in topological insulators, in particular my former PhD students that are now distributed in Europe, and for photoacoustic Augusto Marcelli, that is now for a very strong collaboration on nanopolus graphene, and my undergraduate student and my postdoc student. Thanks a lot.
Thank you, Stefano. We have a very, very short question.
In terms of energy efficiency, how does it compare with a normal loudspeaker?
Actually, we pump with a few milliwatts, and the efficiency is around 2%. In general, commercial loudspeakers are, the power, the electric power is in the watts range, with more or less the same efficiency.
The same efficiency.
Yeah, but you have a factor of 1,000 in terms of energy.
In the first part where you show the phonon, even before the plasmon, the phonon was a little bit asymmetric. So this is the Drude.
This is the Fano interaction with the Drude.
Yeah, but in this case, these are because if you want the 2D, the Dirac system is on the surface.
Yeah.
Whereas here the phonon, you say that are the bulk phonon.
Actually,
why the interaction? Is the Fano decreasing with an increasing number of layers in this case? Because
this is a difficult thing to say. In general, we think that this is the the point is that this frequency more or less corresponds to the bulk phonon, but we think that this is actually an optical surface phonon. So you have really an interaction at the surface between the optical surface phonon and the surface.
You estimate the effective charges of this phono compared to the one of the bulky system?
It's difficult to obtain, an insulating bulk. In order to eliminate the Dirac surface density, you should, for example, dope the system by indium, but you change also the lattice. So in that sense,
you have such a thick system where
in general, over 100 nanometers, you lose a lot the topological properties. So it's a trade-off, very, very complicated in that sense.
We have another question by Harry.
Quickly, what about the role of the curvature in this graphene sponge or nanopods?
It's an open question.
Because dispersion of the cone or also the funnels can change in the presence of nanoscale curvature.
Actually, we are measuring by local nanospectroscopy in the infrared locally the phonon, the graphene phonons by changing the position in a flat region with respect to the strongly curved region. But it's actual research.
Okay. Thank you very much.
Thank you.
Now, next order is